Hi, everyone. Welcome to Lecture 11, Mitigation Strategies for Transportation. So in this lecture, we're going to be looking at ways to mitigate against global warming from the transportation sector. And as an outline, we will be talking about energy consumption, basically energy usage by the world, and how it's changed in recent decades and how it varies across the world. Transportation and emissions. So we look at the relationship between transportation and greenhouse gas emissions. Fuel efficiency, basically a measure of how much distance one can drive on a certain amount of fuel, and the units of that and how that is affected by different factors, okay? How it can be improved, because improving fuel efficiency reduces emissions of greenhouse gases, improves air quality, saves you money, okay? Peak oil, a concept basically saying when half of the oil ever existing has been extracted and consumed, and there's one half left, oil production will peak and then will decline, and costs could rise after that. Another reason for alternative fuels for transportation, alternative to oil. Overwhelming majority of energy for transportation is derived from petroleum or crude oil. And when you burn products made from petroleum, like gasoline, diesel, jet fuel, puts greenhouse gases into the atmosphere. So the reading for this lecture is chapter 7, pages 1 through 65. So there's a lot of good information in chapter 7. You will see some of the same figures, a lot of really useful figures that you can learn a lot by looking at. So fossil fuels, we have talked in lecture 10 about how they were used for generating a lot of the world's energy. Extraction, basically the removal, and combustion, the burning of fossil fuels, accounts for 65%, close to 2/3 of anthropogenic or human-induced greenhouse gas emissions, okay? Burning of fossil fuels for electricity, burning of fossil fuels for transportation, burning of fossil fuels for industry to manufacture products. And the remaining 35%, a little more than a third, comes from changes in land use and agriculture sources, okay? So changing land use, deforestation, for example, as well as agricultural sources. And fossil fuels today provide 84%, more than 4/5 of the world's total energy production. So the book talks about basically banning the use of fossil fuels would stop the world. It can't be done overnight, okay? But there are mitigation strategies that will allow the world to transition from fossil fuel-based energy sources to renewable or alternative energy sources, okay? And most of the energy for transportation is derived from fossil fuels, okay? So how has energy consumption changed over the last 3 decades? Over the past 30 years, global energy usage has increased by about 2% per year. And today, world population is approaching 8 billion. 30 years ago, in 1991, it was a little over 5 billion, okay? So it has increased, and more people means more energy used, okay? So the main reasons energy usage has increased are population growth, we just mentioned, as well as economic development. A lot of countries have grown, have developed during this time, from the 90s on into the 2000s and 2010s. And so that is another reason. there isn't a whole lot of change in energy usage per capita or per person. So when you hear per capita, it basically means per person. You can find energy usage per capita by taking, for a country, by taking total energy usage and dividing it by population. And that can be useful to look at because different countries have vastly different populations. Okay, so you look at energy usage or greenhouse gas emissions for a country and compare it to that of another country, that can be useful, but not always. It won't always tell you the whole story, okay? Because some countries are much smaller, right? Have a fraction of the population, so you won't be able to. You can see more if you actually look at energy usage per capita. And by the way, less energy is required to stimulate a given amount of economic activity. Okay, so in fact, calories per gross domestic product, the amount of energy it takes to generate economic revenue, has declined. Okay, so now we're going to be looking at some figures. Here's a figure from your book, figure 7.1, showing global greenhouse gas emissions on the left from 1970 to 2010, so this 40-year period, and world energy consumption on the right, basically for the same period, slightly different, starting a year later and ending a year or two later, but close to the same time period for both of these figures. And the units on the left for greenhouse gas emissions are basically gigatons of carbon dioxide per year. And a gigaton is 10 to the 9th metric tons, or 1 billion metric tons, and a metric ton is about 2,200 pounds, a little more than an English ton, so a lot. And on the right, we have e-calories per year, basically 10 to the 18th calories per year, okay? And so, as you remember, most of the anthropogenic greenhouse gas emissions in the world are from carbon dioxide, CO2, but not all. So we have some from methane, CH4, you see that here, some from nitrous oxide. And basically, the units will show emissions for those greenhouse gases in equivalent units that would be equivalent for that amount in CO2. Okay, so what do we see here? And it's helpful if we focus on one figure at a time. So let's look at the one on the left, showing how carbon emissions globally have changed from 1970 to 2010. Well, they've increased, right? In 1970, if we look closely, we see that global carbon emissions were around 2.75 or so gigatons of CO2 per year. And by 2010, they're approaching 5 gigatons of CO2 per year. So that's not quite a doubling, okay, but getting close to that. Okay, if we look further in time, we went forward a few more years, we may see a doubling since we would probably see a doubling since 1970. And what's nice about this figure on the left is it actually divides the emissions into relative greenhouse gases, and also for CO2, the principal sources of it. So as you see, major source of CO2, total greenhouse gas emissions, not for the world, not surprisingly, it's burning of fossil fuels, which puts CO2 in the atmosphere, as well as CO2 from land use. Again, most of the anthropogenic greenhouse gases emitted in the world are from CO2, but CH4, methane, makes up a certain percentage. We talked about the sources of that: growing of rice, natural gas extraction, nitrous oxide, agriculture sources. And then very recently, we're starting to see a greater amount of emissions coming from HCFCs, PFCs, and SF6, sulfur hexafluoride. And these HCFCs and PFCs are replacements for CFCs. Remember, they were depleting the ozone layer several decades ago, okay? But the replacements can act as greenhouse gases, although you see a small sliver, very small total amount of the world emissions comes from those. Then we can look at energy production in 10 to the 18th calories on the right, okay? And that has also increased, okay? 1971, in that particular year, the world used more than 55, not quite 60, 10 to the 18th calories per year. By 2012, world energy production was up to 130 or so, 10 to the 18th times 10 to the 18th calories per year, which is more than a doubling, okay? So the figure on the right actually shows where that energy, okay? So those three fossil fuels, coal, petroleum, or crude oil, natural gas, make up a great percentage of the world's energy that's produced and then consumed, okay? So it used to make up a greater percentage. Notice in 1971, small fraction of the energy production was from sources other than these three fossil fuels. For example, in kind of the gold color, biofuels and waste, and in the light blue, hydro, dams for electricity, for example. But by the time you get to 2011, 2012, greater amount of the world's energy is made from hydro, biofuels, and waste, and other renewables. Now, yes, it looks like a very small sliver, okay? But don't get dismayed. In the last 10 years or so, since 2011, there's been a great development in renewables, okay? Solar, wind have really grown, especially in certain countries, okay? So those are growing and making up more of the world's energy production, especially for electricity. Don't really have cars that run simply on solar panels yet, but we do have cars, okay, Tesla, Chevrolet Bolts, that are run on electricity that can certainly come from solar, okay? So, moving on, energy consumption per capita, okay? So again, coming back to that idea of what if we took energy usage and divided it by population, okay? And we're looking at energy consumption per capita from the early 80s into the early 2010s for three major countries in the world, in terms of population, economic power, as well as the world as a whole. So the US energy per person, usage per person in gigacalories, which would be billions of calories per person each year, okay? Now, over this 30 plus year period for the US, it doesn't change a whole lot. You do start to notice it come down from actually the late 70s and the early 80s, and then it slowly increases in the 80s and the 90s, but it has been coming down a little bit, okay? But what do you notice that's different about the US compared to Japan or China? Basically, it's just saying that the average American uses far more energy than the average Japanese or average Chinese, okay? And so basically, energy consumption per capita in the US has hovered between 75 to 85 or so gigacalories, right, per person each year, right? Whereas in the world, it's much lower. For the world, in the 80s and 90s, it was below 20 gigacalories per person each year. And it's increasing a little bit to 20 or so, but that's still roughly a fourth of what the average American uses. So the average world citizen, human, uses 1/4 of what the average American uses as of 2011, 2012, okay? And it average Japanese uses about half of what the average American uses. And it's very interesting if we look at China's energy consumption per capita. In the 80s and 90s, it was far less than the US. Um, and so it's kind of interesting because China is the top emitting country, okay, emits the most CO2. And then in the 2000s, China was rapidly developing, installing a lot of coal power plants. So you do see that. You see that in starting in around 2000 or so, in the early 2000s, and continuing to the mid to late 2000s, into the early 2000 teens, the increase in energy usage per person, although still far less than the US. So keep that in mind, although China gets a lot of attention about being the top emitting country and how their emissions are rapidly increasing in the 2000s, still per capita, far lower than US. Okay, so that's important to keep in mind. Okay, we can also look at energy consumption per gross domestic product. Okay. Basically, we're looking here at how much energy it takes to generate $1 of economic revenue. Okay. And the units are megacalories or millions of calories per dollar. Okay. And you notice how it's come down over time, similar time period as the last figure. Okay. And so basically what we're saying is that it takes less energy to generate economic revenue, which is good. Okay. Is that less energy means less emissions, basically. Okay. And you do notice for China, it used to take a lot more energy to make economic revenue. Okay. In the early 80s, it took about 8 million calories to generate $1 of economic revenue in China, compared to 3.5 in the US, 2.5 for the world. But in the 80s and 90s, China was able to greatly reduce this. And so by the time we get into the early 2000s, it's similar. It's a little higher, but it's close to basically how much the energy consumption per gross domestic product of US and world. Okay. See Japan standing out though as for these three countries and the world as a whole for these years, takes the least amount of energy to generate gross domestic product. So on final look here at these figures, again, we notice how carbon emissions, not just from CO2 and CH4, but emissions as well as from nitrous oxide and HCFCs, PFCs, SF6, any others, how they've increased. Okay, so now an energy consumption, production and consumption has also increased. So now focusing on transportation. Globalization of the world's economy requires that humans and products move long distances. Okay, and in the last few decades, the world has really become globalized. People travel long distances. A lot of people, some of you watching this may have traveled out of the US, okay, or from your home country, okay, if it wasn't the US. And goods move long distances. Okay, products can be made overseas or in countries thousands of miles away and then shipped. Okay, passenger and freight travel will continue to increase during the next 30 years. And by 2051 or 52, which would be years from now, close to mid 21st century, inflation is going to be higher. Okay, it's getting close to 8 billion. By 2050, it could be 10, 11, 12 billion. Okay, and that's another reason that travel will increase. Not only people and goods moving longer distances, but more people and more goods moving. Okay, so both population increase and longer travel distances. Okay, leading to the increase in passenger and freight travel. And so now we're going to be looking at figures showing how passenger and freight travel could have changed in the early part of this 21st century and could change in the next few decades, total as well as for different regions of the world. Okay, so on the left, we're looking at human travel in units of trillions of people per kilometer, kilometers, 0.62 miles per year, okay? And on the right, freight travel in trillions of tons, okay, per kilometer per year. Passengers, yeah, so the units are for human travel, trillions of passengers times kilometers, not per kilometer, times kilometers. Okay, so it's looking at the effect of both people and distance, multiplying those variables. And then freight travel is trillions of tons, okay, weight basically times kilometers, distance per year. So in 2000, human travel in these units, more than 30, okay, low 30s, 32, 33 trillion people times kilometers per year, okay? And by 2050, you see here, it could increase to 75 trillions people kilometers per year, okay? So it more than doubles according to this graph. And freight travel basically triples from 2000 to 2050. From in 2000, just under 15 trillion tons kilometers per year to just over 45 trillions tons kilometers per year. Okay. So freight travel increasing at a faster rate, you can see that. And then we can also look at what regions of the world have the most travel. Okay, so if we focus on the left here, looking at human travel, okay, you can look at which colors make up the greatest widths, which colors make up the greatest portions, okay? And you see the kind of maroon, dark red, that's North America. You see the kind of dark green, that is Western Europe, right? You see the purple, that is for China, okay? And then you see some of the smaller, basically contours, smaller sections, such as the gold Eastern Europe, less human travel there, as well as in the Middle East, okay, shown in red, okay. Then we could also look at relative contributions of freight travel. Again, North America, Western Europe, China making up big percentages. And actually, compared to total freight travel, very little in Eastern Europe, in the Pacific, on the continent of Africa, okay, although it does increase, okay, as we go forward. So petroleum, currently the overwhelming energy source for travel. Today, about 90% of the world's energy for transportation is derived from petroleum, okay? And the top 3 petroleum producing countries are Saudi Arabia, the US, might surprise you, and Russia, okay? Talk more about this when we talk about gasoline and oil and prices, and production, okay? But actually US oil production had increased years ago. How many years of oil is left in the world? Okay, any ideas? Think about that question, okay? So now looking at a figure in the book showing petroleum production by region from 1980 to 2014 or so, okay, so about a 35-year period. And the units are petacalories per day. That's 10 to the 15th or quadrillion calories per day, okay? And so interestingly, we're looking at total petroleum production again for the world and then dividing it by regions. It actually decreased from 1980 to 1983. Okay. There were oil crises in the mid 70s. A lot in the world, a lot of effort to make smaller vehicles, use less oil, drive slower. We'll talk about how speed affects fuel efficiency and oil usage. But then it has increased since the mid 80s. Okay. And which regions of the world have the most oil production? Okay, you see the brown color for Middle East, a lot of OPEC countries there. OPEC stands for Organization of Petroleum Exporting Countries, that exported to other countries that basically exported to other nations. Green, you see Europe and Eurasia, so Western and Eastern Europe. And then blue, you see North America, okay? And you see the red shading for South and Central America, okay, so Latin America countries, and it might not look as large, as much, there's not as much oil produced there total as for North America or the Middle East, but there are a lot of important countries there that export oil, including to the US, such as Venezuela, Colombia, okay, so we'll talk about that too. Okay, so about 14% of global emissions, greenhouse gas emissions, come from the transportation sector. So that's about 1/7. Okay. And in the US, it's closer to 28%. In fact, as we talked about in lecture 10, transportation has passed electricity generation as the top source of greenhouse gas emissions in the US. Okay. In China, it's still only 7%. A lot more of China's emissions come from electricity generation, okay, such as from coal power plants, and industry, okay, a lot of goods made in China, okay. When we talk more in lecture 12 about mitigation strategies for electricity generation, we'll see how China's gone more green in recent years, okay, include building large solar farms, pledging to keep their emissions by 2030, I believe, if not sooner, okay. So light duty vehicles, basically personal vehicles you drive to school, to work, okay, or that you did before the pandemic, right? Maybe some of you are working, some of you are in person, going to the office. Some of you are taking in-person classes. Some of you are taking online synchronous classes. There's also asynchronous online classes. Freight trucks, okay, so basically tractor trailers, semis that carry goods, and airplanes contribute the largest shares, okay? And there's not just airplanes used to transport people, but goods too, okay? UPS Airlines is an airline transporting packages, okay? And there's lower total emissions from boats, ships, trains, buses, and motorcycles, okay? And emissions from all modes of transportation, except buses, are climbing at about 2% per year, according to the book. So because light duty vehicles contribute, actually, we'll see the largest share out of all these modes of transportation, one strategy for greenhouse gas abatement is to improve the fuel efficiency of light duty vehicles. Okay, so we'll talk about that. So now, looking at transportation emissions, how transportation emissions have changed recently and may change by 2050, okay? And this is a figure from the first edition of the book, which was published in 2010. So it is a little older, but it shows some trends we may expect in the future. And it shows you carbon emissions. Okay, so remember how before we were looking at total world greenhouse gas emissions and how they could change in the first how they've changed recently and may change in the future. Now we're actually looking at emissions solely from transportation, which makes up 14% of global emissions, and breaking it down into modes of transportation. And so what you see is that all these methods of transportation we all have here, 2- and 3-wheelers, motorcycles, trikes, buses, freight and passenger rail, so trains, water, ships, airplanes and helicopters, freight trucks, light-duty vehicles. Light-duty vehicles make up the largest share. In 2000, around 43% of all transportation emissions were from light-duty vehicles. And now if you take those 3 sources mentioned on the previous slide that make up the greatest contributions, light-duty vehicles, freight trucks, and airplanes, they're responsible for close to 3/4 of the emissions. Okay, so less emissions from motorcycles, okay, buses. Now, true, buses can be large and more polluting than the cars, far more, but there's a lot more cars on the road than buses, okay? So as we go forward in the next few decades, it does look like emissions from transportation could increase, okay, from these different sources, okay? Although some more than others, okay, maybe not a whole lot for freight and passenger rail. It doesn't look like it's becoming that much thicker over time, does it? Same with buses, okay? Buses are becoming cleaner. Hybrid buses, natural gas buses, okay? So we did look at this figure in lecture 10, but it's useful here because we're talking about transportation. And in fact, we kind of have a couple figures. So we looked at the slide, I should say. But on the left here, we have US transportation sources, okay, as of 2017. So this is pretty recent data. And then we have, for that same year, transportation energy usage by type. So if we look at the pie chart on the left, what we'll see is that 89% of the energy used for the transportation sector in the US comes from petroleum, okay? 55% of that energy usage is from gasoline, more than half, gasoline to power cars and trucks. 22% is from diesel or distillates, but basically diesel. Diesel can be used in trucks, vans, buses. Jet fuel makes up 12%, about 1/8, and jet fuel is also made from petroleum or crude oil. And then we do have some alternative sources. Natural gas, 3% of the energy usage for transportation. That's gone up. Biofuels makes up 5%. That includes ethanol, biodiesel. And then other, number 3, that includes electricity, okay? And by the way, in 2007, just 10 years before this year, okay, so that's 2007, 14 years ago, closer to 95% of the energy usage in the US, of the energy usage for transportation, was from crude oil, okay? So it has gone down, okay? Tesla really started becoming more popular in 2012. Natural gas buses have become more popular, okay? Some hybrid buses have started replacing those diesel buses for certain fleets. Even VTA has a few fully electric buses, okay? So, which are quiet. And oh, by the way, San Francisco, their buses, some of them are powered solely by electricity. Okay, so some of the Muni buses have the cables, right? They have their antennas that are attached to electric lines. Okay, and same with buses in Seattle, which are part of the King Metro system. So transportation energy usage by type on the right, light trucks, cars and motorcycles, and then larger trucks make up, if we do the math here, 32 plus 24, 56 plus 23, 79%, close to 4/5 of the energy used for transportation in the US is from personal vehicles, motorcycles, larger trucks, okay, with smaller contributions from other modes of transportation, including what we've been talking about on previous slides. So, fuel efficiency, okay. How would you define fuel efficiency, right? So if you need to, can take a few moments, think about that. You can pause the video. And what are the units of fuel efficiency? So fuel efficiency is defined basically as the distance traveled divided by volume of gasoline required for that distance. Most of the time we think of it as that. You might substitute diesel for gasoline, okay? But most of the cars in the world, the US and the world still run on gasoline, okay? It's changing, okay? And it's commonly measured in units of kilometers per liter for most of the world, because most of the world uses the metric system for measurements, or miles per gallon in the US, okay, which has the English system as the official system of measurement, along with Liberia and Burma or Myanmar. And think about the benefits of improving fuel efficiency. What are benefits of having a higher fuel efficiency as you drive? Okay. Well, if your fuel efficiency is greater, okay, you get more miles per gallon. That means you can travel on the same distance, on less gasoline, right? If you have a higher fuel efficiency, you don't have to burn as much gasoline to go this certain distance, right? Well, that saves oil, right? It saves gasoline, which is made from oil, preserves oil, which is running out, okay? Saves greenhouse gas emissions, right? You don't have to burn as much. Improves air quality, right? Less tailpipe pollution. And then maybe the biggest benefit or the most appealing benefit to you, saves you money, right? Especially right now, we're going to talk about gas prices, but the Bay Area, right? They're over $4, close to $5 per gallon in some locations, right? So there are different factors that affect fuel efficiency of light-duty vehicles, personal cars, and trucks. And it varies by region of the globe. Here are some of the factors affecting fuel efficiency. And if you want, you can pause and think about some of them too. Driving conditions. Basically, how you drive actually greatly affects fuel efficiency. Your speed, as well as highway versus city driving. We'll talk about this. Taxes on petroleum and vehicles. There's a relationship between vehicle fuel efficiency and the taxes on it, as well as taxes on petroleum. Okay. Consumer preferences. What kind of vehicle would you prefer to drive? Okay. A sports car, which can go really fast, right? But doesn't have as high fuel efficiency, or a hybrid, okay, which is much better for reducing emissions and saving you money on gasoline. Use of diesel-powered vehicles. In fact, in some Western European countries, a lot of the new cars are actually running on diesel. And diesel has improved in last several decades. Used to be in the US, for example, trucks would run on diesel and they would be noisy, sometimes kind of rough rides in them, and also in a thick, dark smoke. Whereas through technology, the newer powered diesel vehicles are cleaner, quieter, okay, and they can actually have higher fuel efficiency in some cases. And automobile manufacturer agreements, okay? we'll talk about the CAFE regulations that were basically developed in the 70s and in the US. And different countries have different regulations where basically the government will say, of a country will say, basically, a certain automobile manufacturer's fleet of vehicles has to reach a threshold for fuel efficiency. So, how has fuel efficiency changed in recent years? Here's a figure from the book showing how fuel efficiency of light-duty vehicles has changed in several Western European countries, as well as Australia and the US. And we have both the metric units of fuel efficiency on the left y-axis or vertical axis, kilometers per liter, and the English units of fuel efficiency on the right, miles per gallon. So in the early 2000s, now, okay, going back 20 years, fuel efficiency in France, Germany, and the United Kingdom, so these Western European countries, was 29 to 32 miles per gallon. Okay, as you can see here, Germany in gold, United Kingdom in green, and France in blue. It has improved, okay? And the US, Australia, and Japan were kind of lagging behind. You see, low 20s mile per gallon range, it has improved, okay? And what do you see how fuel efficiency for these countries here changed from the 70s into the 80s into the 90s? For many of them, it increased, okay? Now notice in these three Western European countries we're looking at, it actually decreased in the 70s earlier, and then it started increasing, okay? In Australia, it's stayed actually fairly stable over the time period. And look, in the US, it used to be much lower. You look here, in 1970, the average fuel efficiency of basically a new car, or a car or small truck sold in the US, was in the low teens in terms of miles per gallon, maybe 13, 14 miles per gallon, really low. Seems by today's standards, that just seems like really like a gas guzzler, right? And it remained low in the 70s, and then the increase in the 80s, okay, as the US started making smaller cars, more fuel efficient vehicles, as well as reducing the national speed limit, okay, to 55 miles per hour. We'll talk about that in a bit. But US fuel efficiency, or sometimes called fuel economy, basically the same, but it's kind of a way of thinking about how it saves you money, right? And we're looking here at average US fuel efficiency or economy for new vehicles. Again, we're talking about passenger vehicles, cars, small trucks, for all model years from 1975 to 2017, okay? By 2018, fuel efficiency of new vehicles in the US had topped 25 miles per gallon. So there are three curves here. Cars in green, trucks in blue, and then combining them in black, okay, in the middle. And not surprisingly, cars tend to have higher fuel efficiencies than trucks. Okay, trucks can be bigger, require more energy to go, right? So in the mid 70s, you notice fuel efficiency of new cars sold in the US, gosh, 14 miles per gallon, trucks even lower. But look at how it rapidly increased from the mid 70s to the early 80s, okay? By the early 80s, new cars sold in the US were getting well over 20 miles per gallon on average, okay? Still under 20 miles per gallon for trucks. And then after the improvements into the mid 80s, from the mid 80s to the mid 90s until actually the early 2000s, fuel efficiency of trucks was slowly decreasing, as well as for both cars and trucks. Cars may be decreasing a little bit for different reasons. Larger cars being sold, maybe demand for more sports cars, okay? But then you really notice in the last 15 years or so how it's increased. So starting in the early 2000s, actually maybe 2005 here, you start to see an improvement. From 2005 to 2017, new cars sold in the US improved in fuel efficiency from about, if you look here, 23, 24 miles per gallon to getting near 30. That's pretty good. By 2018, new cars sold in the US averaged 30 miles per gallon. For both, it was up over 25. And even trucks have passed 20 miles per gallon. Okay, so the average fuel efficiency of a new truck sold here in the US, it's in the 21, 22 mile per gallon range, which is much better than it used to be. So good news. Now, how does fuel efficiency relate to speed? Okay, due to increased wind resistance at higher speeds, fuel efficiency starts to decline at speeds above 50 miles per hour. Okay, and the book mentions this. Through technology, though, that threshold where fuel efficiency starts to go down with higher speeds, it's actually gone up to more like 55 to 60 miles per hour. Okay, so you might make a note here. For the newer vehicles, new cars and trucks sold in the US, you actually can get to about 55 to 60 miles per hour before fuel efficiency starts to decline. And vehicles traveling at 75 miles per hour are roughly 20% less efficient than those traveling at 55 miles per hour. Okay. All else being equal, weather, terrain, say if you had one car, and everything else was equal. Okay. And so 20%, you can think about how you could save money on gasoline. Okay. So the speed on a lot of Bay Area freeways is 65 miles per hour, right? So if you were driving in the slow lane, the lane on the right, or the second to the right lane, I'd say even 60 miles per hour, you actually be greatly improving your fuel efficiency compared if you were driving the fast lane at 75 to 80 miles per hour. Okay. This is another reason, by the way, actually, we'll talk about to not speed in addition to for safety, right? To be safer, take it, slow. You can really improve fuel efficiency. And I've noticed it. Personally, I have a 2019 Prius, and if I'm driving in the quote unquote slow lane, say on cruise control, okay, at 55 to 60 miles per hour, and the newer cars, right, have adaptive cruise control, which is really helpful because it will basically, the adaptive cruise control, it's helpful if there's not too much traffic. If there's a lot of traffic, right, braking, you don't want to use cruise control, right? But if there's not as much traffic, the adaptive cruise control will keep the car at a speed so that it stays a certain amount of car lengths behind the car in front. And if you remember, from some of you are young, you may have only had your license a few years. The California DMV handbook says basically for every 10 miles per hour should be one car length. So if you're driving at 60 miles per hour, you should have 6 car lengths in front to the car in front of you, right? And now, unfortunately, right, that's doesn't always happen, right? It's, there's tailgaters, right? That's another story, right? But anyway, so you can notice that. So coming back to talking about Prius, if I'm driving at 60 miles per hour on cruise control, or, and maybe I set the cruise control to like 61, 62, but, it sometimes be a little slower if the car in front is slower because I have adaptive. But if I'm going 55 to 62 miles per hour, and I can get on the freeway without a lot of braking, pretty constant in that range, I can get over 60 miles per gallon. Okay. Now, if I'm driving at 75 miles per hour in the fast lane, or my fuel efficiency is going to probably be under 50 miles per gallon. Okay. So definitely under 50 miles per gallon. So in 1974, the national maximum speed limit law was enacted by Congress. Okay, so 48 years ago, the national maximum speed limit law was enacted by US Congress. And that was after the 1973 oil crisis. In October of 1973, there was a war in the Middle East, the Yom Kippur War. And basically Egypt and Syria were at war against Israel. And the US has been an ally of Israel for a long time and sided with Israel. And some of the OPEC countries, Organization of Petroleum Exporting Countries in the Middle East, disrupted supply of oil to the US. Okay. And so there were higher prices, supply disruptions, long lines of a gas station. There's a picture of that, a long line of a gas station. And depending on the day of the week, you might, and your license plate, whether it began with an even or odd number, you might only be able to buy gasoline, certain times. Okay, you might be your parents or your grandparents may remember this. And what that national maximum speed limit law did was set a maximum speed limit, believe it or not, at 55 miles per hour. Okay, and this remained in place until 1987. So from the mid 70s into the mid 80s, on all the US freeways, the maximum speed limit was 55 miles per hour. And for Californians, that might seem really slow. Okay, in rural California on I-5, the speed limit is 70 miles per hour. Okay, and it depends on the state. In Oregon, their maximum speed limit tends to be more like 60 miles per hour. Okay, and Oregonian drivers are, in some polls, ranked as some of the nicest of drivers. Okay, depending on your perception, you might think them as real nice. They, you stop at a light, you don't go right away. They're not going to honk. Maybe they won't honk at you, but by your standards of some in California, maybe they're slower. Okay, in 1987, that speed limit was raised to 65 miles per hour. It was very unpopular, and the law was repealed entirely in 1995. Okay. Also interesting that, how on all the California freeways, you see the sign that says speed limit 65, and then sometimes you'll see another sign that says trucks 55. In Arizona, the speed limit on a lot of their freeways is 70, but there's no restriction for trucks. Okay. So what's the highest posted speed limit in the United States of America? Any ideas? 85 miles per hour on Highway 130, State Highway 130 in Texas. There's a stretch of this highway, about a 40-mile stretch or so, where the speed limit is 85 miles per hour. 85. And the reason it's so high is because it's a very rural road, very few cars on it, not a lot of crossings or merges. Okay, so if you're interested. In San Francisco, where, it's parts of San Francisco, right, doesn't have a lot of freeways. And so the few freeways there are, like 101 and 280, okay, they can actually, the speed limit might only be 45 to 55 miles per hour because they tend to be more congested. Now, this figure from the book, figure 7.13, shows fuel efficiencies in kilometer per liter of representative vehicles in the United States as a function of speed in kilometers per hour from various studies over the decades. And yeah, I know the units are metric, okay, but you can still see some trends here. First, if we look here at the older vehicles in green from 1970 or earlier, they had far lower fuel efficiencies than the vehicles from the early 80s in blue, the vehicles from the late 80s to late 90s in red, and the newer vehicles manufactured in your lifetime. Okay. And what you see here is that you reach a certain speed here, and basically fuel efficiency starts to decline. For the older vehicles, it might only be 60 kilometers per hour, which is somewhere around 45 miles per hour. But for the newer vehicles, like I was saying earlier, you can actually start going closer to 55 to 60 miles per hour before fuel efficiency decreases. Now, speed, although important, is second to driving behavior in determining fuel efficiency. Okay. Book says that worldwide, number of vehicles and distances they travel are many times greater than just a couple decades ago, but the construction of new roads has not caught up. And this has led to more congestion. Okay, the book says that the US paved a large portion of roads during the past 50 years, but has extended the total length of roads by only 15%. And, during 2020, from early to late 2020, right, traffic patterns were, different, right? When we were all staying at home, there was very little traffic, right? And of course, traffic has picked up again. And really in the Bay Area, it's increased over the past 10, 15 years, okay? Quick acceleration and heavy braking decrease fuel efficiency by over 30%, okay? By the way, there's different reasons for that, why traffic's increased. More people, longer commutes. Some people have, the Bay Area has kind of expanded for some. There's people that commute further. I've had students I've had at least a couple in recent years that live in Modesto and would commute to San Jose State, and so hats off to that. It's a long commute, even if just a few days a week. Quick acceleration and heavy braking decrease fuel efficiency by over 30%. That's why automobile companies advertise two efficiencies for each car, okay? If any of you have ever bought a car in person, and went to the dealership and looked, there's a piece of paper on the side, it'll give you two values, two numbers, miles per gallon. It will give you a city MPG and a highway MPG. And generally, for gasoline-powered vehicles, the highway MPG is anywhere from 2.3 to 7.8 miles per gallon more, okay? And that's because when you're driving on the highway, you're not braking as much, you're not accelerating as much, right? Whereas if you're driving in the city, you're stopping at lights, you're having to accelerate. And again, heavy braking and quick acceleration take fuel efficiency down, okay? And due to the number of cars increasing faster than road capacity, congestion is rising, okay? And that could unfortunately take fuel efficiency of highway driving down, because if you're driving on the highway and you stop and go, your fuel efficiency is going to be lower, okay? There's been efforts to address this, widening roads. In recent years in the Bay Area, what have really shown up on the freeways like I-680, 880, 101, or are being installed, the new fast track lanes, okay? And some of them are replacements for carpool lanes. For different reasons. For some regions, the carpool lanes were starting to become more congested, with not just carpoolers, but also the vehicles that have the sticker, like some of the hybrids and electric vehicles. But the issue with the fast track lanes is you have to pay to use them unless you have 3 people. For some of them, you have to have 3 people, and then you have to have the fast track responder, and then you can go in them. But wanted to point out, we'll talk about this more when we talk about hybrid vehicles, but actually hybrid vehicles can actually have higher city fuel efficiency than highway fuel efficiency. And that's because regenerative braking, okay, hybrids actually generate energy for the battery charges during braking. And hybrid vehicles can actually have a higher fuel efficiency at lower speeds, more like 40 miles per hour compared to 60 miles per hour, okay? So we'll talk more about that, and hope this helped, and that you learned a lot from this lecture, and we will continue with more of lecture 11 um, in the next video during our next class. So thank you very much.